Okay, so hi everyone. Welcome to our next installment of the GROOT seminar. Today we'll be hearing from Baylee Schutte, who will be telling us about the projective span, the line field problem. Take it away.
Hello, everyone. I just want to start by thanking the organizers for doing all the invisible work needed to put this on. I'm really excited to have a chance to talk a bit about some work in progress. I thought by now it wouldn't be in progress, but it's still not finished. And I just want to say also, this is like really properly joint with my supervisor, Mark Grant. Let's see. So the plan for today is, first of all, the vector field problem has a very, very long history. So I want to kind of put my projectivized version in its classical context. And I'll, of course, introduce the main objects of study. Then we'll go through some kind of easy, but hopefully still interesting projective span computation, so we can all kind of get to grips with it. And then comes the hard part of the talk. In Stong's book on cobordism theory, he has this funny paragraph where he's talking about differential topology, and he says differential topology is the subject where topologists study differentiable manifolds using any methods that they can possibly find. And I just really relate to that. And my methods are obstruction theoretic, in particular non-simple Moore-Postnikov theory. So I'm going to try and give a really accessible and distilled overview of how to use Moore-Postnikov theory to solve a lifting problem. And then very briefly, I'll just tell you about some preliminary results that will hopefully interest you. So to start, my project is in the intersection of geometry and algebraic topology. And the sort of prototypical result of this arena is Hop's theorem, where you have a compact n-dimensional manifold, and it emits a non-vanishing vector field, so a vector field without any zeros, if and only if the Euler characteristic vanishes. And you might be more familiar with the Poincaré-Hopf index theorem, which says maybe you have a vector field on a manifold with some zeros. You then calculate like an index around each of those zeros and add them up, and then you get the Euler characteristic. And you can remove those zeros by like perturbing the vector field, if and only if the Euler characteristic vanishes. The reason I'm stating this theorem in its sort of older and less precise form is because the spirit of my project isn't about computing some kind of specific index. It's just about finding necessary and sufficient conditions for such an index to vanish. So hopefully that will become clear later, but let's set up some necessary nomenclature. Give yourself a smooth n manifold. Recall that a vector field on that manifold is a smooth section of the tangent bundle. So in other words, the tangent bundle gives you, for every point on the manifold, the tangent space at that point, and a section will assign to every point on the manifold a vector in the tangent space at that point. And the vector bundle data just makes sure that that choice is continuous and smooth and whatnot. We will say that M admits a k-frame if there exist k linearly independent vector fields on M. So you can think of a k-frame as, for every point on the manifold, you assign k tangent vectors, and those k tangent vectors need to form like an n by k orthogonal matrix if they're linearly independent. And finally, we define the span of a manifold to be the maximum k such that M admits a k-frame. So we're going to have to think of it like this. So we really want to think of every vector field as corresponding to a trivial line subbundle of the tangent bundle. We'll get a lot of intuitive mileage out of this idea. So if the span of a manifold is at least k, then the tangent bundle splits off a rank k trivial subbundle, which I'll denote like this. So var epsilon means a trivial line bundle, And then the superscript indicates like the k-fold sum of those line bundles. And this xi here is just like the leftover rank n minus k bundle. The central problem of k-frame theory is to express the span of a manifold in terms of familiar algebraic invariants, whatever that means. The kinds of invariants are usually like the dimension of the manifold or characteristic classes of the manifold, the Euler characteristic, things like this. This problem, maybe here I'll just say before I move on, that this problem has pretty much been solved for manifolds of dimension 7 and lower. Although, you know, so there's a lot left to do, but at least for low dimensions, we do know something. This table gives, for example, necessary and sufficient conditions for an n manifold, where n is arbitrary. I'm just assuming it to be bigger than 4, to be greater than or equal to 2. So I'll try and talk you through this table. This is the oriented case. So I'm additionally assuming that M is orientable and it's sufficiently nice, which means smooth, closed, and connected. If you can kind of focus in on the odd dimensional case, so when n is 1 mod 4 and when n is 3 mod 4, in that situation, for odd dimensional manifolds, the Euler characteristic is always 0. So by Hop's theorem, we know that there exists at least one vector field on the manifold M. In the case n is 1 mod 4, we need the n minus first Stiefel-Whitney class to vanish, and we also need the real curvaire semi-characteristic to vanish. And I won't explain what this is, but the idea of a semi-characteristic is when you don't have an Euler characteristic to use for anything, because it's 0 in this case, a natural substitute is a semi-characteristic where you take the alternating sum of the Betti numbers and add them up through the middle dimension. So, and then you take that sum mod 2. It doesn't really matter, but that's, you know, something that kind of comes up a lot. And in the case that n is 3 mod 4, amazingly, M always has a 2-frame. And this is a highly non-trivial result that appeared in an Annals paper by Thomas. And then in the case when n is even, so we have n is 2 mod 4 and 0 mod 4, we of course require that the Euler characteristic vanishes because of Hop's theorem. And in the case that n is 0 mod 4, we also require that the signature of the manifold vanishes mod 4. And I also want to explain what this signature thing is, but just to give you an idea of how powerful of a gadget it is, Milner in, I guess, probably the late 50s, I think, he, you know, won this Fields Medal for constructing the first ever exotic 7 spheres. And the way he does that is he basically defines a sort of modified signature for an 8-dimensional manifold whose boundary is a 7 sphere. So anyway, this signature thing is like, it's just a really powerful classical gadget. I won't explain too much about the non-orientable case, but we do also have some information when the manifold is non-orientable. So when n is even, you require the twisted Euler class to vanish and the integral twisted n minus first Stiefel-Whitney class to vanish. This was first proved by Koshorka in his crazy book, and no one really read, I think, the part that had this in it. So Polina later proved this using different methods. And then we know stuff in the other cases, but I won't explain this. Now for me, as I said at the beginning, I'm studying a projectivized version of this vector field problem. So mutatis mutandis, as opposed to a vector field, I'm interested in line fields on manifolds, which we can think of as smooth sections of the projectivized tangent bundle. So the fiber of this bundle is like real projective space. And so we say that M admits a projective K-frame if there exist K linearly independent line fields on M in exactly the same way as before. And so we define the P-span or the projective span of a manifold to be the maximum K such that M admits a projective K-frame. So for example, P-span of the manifold is at least K if and only if the tangent bundle splits off k possibly non-trivial line bundles. These eta here, eta i's are the non-trivial line bundles. And I should also just mention that if the tangent bundle splits completely as a sum of line bundles, we then say that M is line element parallelizable, as opposed to just parallelizable. So, okay, let's have some examples just to get comfortable with this pspan thing. The first important observation is if we have an n manifold, pspan can't be the dimension of the manifold -1. And here's, I mean, this isn't like a rigorous argument, but this is just to convince you. Just say, okay, the tangent bundle does split off n-1 possibly non-trivial line bundles. You see, oh no, there's a line bundle amount of information left over. So actually the tangent bundle splits completely as a sum of line bundles and the manifold is line element parallelizable. So that can't happen. Another quick but very important observation is that pspan is always at least the span of a manifold. And here's a way of thinking about this. So if the tangent bundle splits off a rank k trivial subbundle, you have k trivial line bundles and each of those contributes to the pspan count. But maybe more directly, you should think of it like if you have a vector field on a manifold, to every point you've assigned a tangent vector, right? Instead of taking just the tangent vector, you can take the line spanned by that vector. So in that way, every vector field gives rise to a line field on the manifold. It just so happens that not every line field comes from a vector field, so pspan might be more than span. This is also a really powerful but very simple observation. If M is simply connected, then the pspan is the same as the span. So this is very, very useful for, say, spheres, right? Spheres are simply connected. And because the span of spheres has been calculated, this is a huge problem, we automatically know the pspan. So I'll just quickly try and convince you of this. It's kind of a nice little argument. Suppose that pspan is at least k. So the tangent bundle splits off k line bundles. We just need to argue that actually each of those line bundles is a trivial line bundle. And this follows because line bundles are completely classified by their first cohomology. The classifying map for a line bundle over M, is a map from M into B01 or like RP infinity, which is an Eilenberg-McClendon space of type Z mod 2, 1. So we can see this. And then using your universal coefficients and the Hurewicz isomorphism, we have this isomorphism here. But we assumed that M was simply connected. So pi1 of M is 0. So this means that every line bundle over a simply connected manifold is trivial. So the tangent bundle actually splits off a rank k trivial subbundle. So the span is at least the pspan, but by point 2 of this slide, we know that the reverse inequality holds, and so actually we have equality. Is everyone convinced? If anyone has any questions, let me know. Maybe I should try and check the chat. I can't see it. Are there any questions? No? Okay. This is the last theoretical example. I hope everyone's doing okay so far. Suppose you have a covering map of smooth, close connected, blah, blah, blah manifolds. Then the projective span of the cover is at least the projective span of the base. This is also a very useful thing. To see this, you have to remember a differential geometry fact. So don't worry if you don't remember it. You can just believe me. So suppose that the projective span of the base manifold M is at least k. So the tangent bundle splits off k non-trivial line bundles. Then we can use this differential geometry identity. The tangent bundle of the cover is the same thing as the pullback along the covering map of the tangent bundle of the base. If you don't remember this, it's just a consequence of looking at the normal bundle of this covering map. It fits inside an exact sequence, and you can just derive this very quickly. But the point is that when we pull back the tangent bundle with this description, the tangent bundle event with this description, the pullback of all those line bundles along the covering map, it's just more line bundles. So each of these is another line bundle. But the point is, the pullback of this rank n minus k bundle, it could split off some more line bundles. So hence the projective span of the cover is bigger than or equal to the projective span of the base. Okay, 2 more examples. These are more concrete, and then we'll be done with examples. Let K be the Klein bottle, so a surface. First of all, the Euler characteristic of the Klein bottle is 0. If you don't remember this, the Klein bottle is doubly covered by the torus. So you can just compute the Euler characteristic of the torus and then divide by 2. But anyway, okay, so the Euler characteristic is 0. So we know from Hop's theorem from the beginning that we have at least one vector field. And to argue that there's only one vector field, the easiest way is to use characteristic classes. So if you're not familiar with characteristic classes, don't worry. There's a couple of facts we need to know about them. First of all, parallelizable manifolds characteristic classes of parallelizable manifolds must vanish. So if your manifold is parallelizable, then all of the characteristic classes are 0. And the other fact is non-orientable manifolds have non-zero first Stiefel-Whitney class. So the fact that W1 of the Klein bottle is non-zero means that the Klein bottle cannot be parallelizable. So we know that span has to be 1. Otherwise, the tangent bundle would be trivial and then it would be parallelizable. We can also quickly compute the p-span using one of these facts that we just learned. So the Klein bottle is 2-dimensional, and we know that p-span of a surface can't be 1 because 2 minus 1 is 1. So we must have that the projective span is 2. Interestingly, though, this is kind of, this sits inside a more general context that I just couldn't help but mention. So if you view the Klein bottle as a circle bundle over a circle, then you can realize the Klein bottle as a solved manifold, which is a homogeneous space of a connected solvable Lie group. It doesn't really matter. I just wanted to mention this really interesting paper by Auslander and Sharba, where they show that every solved manifold is line element parallelizable. So you could deduce that the Klein bottle is line element parallelizable using the results of this paper, although it was a bit overkill. Finally, this is a final example. I want to compute the projective span of real projective space for you. But before I do that, I just have to quickly tell you about the span of spheres. This is kind of a famous story. Hurwitz and Radon calculated a lower bound for the span of spheres in terms of these Hurwitz-Radon numbers, whatever they are, it doesn't matter. And then Adams famously showed that, oh, well, the lower bound is actually the upper bound. And then he calculated the span of spheres. And he did this using K-theory and Adams operations. The next thing that you can do is you can show that the span of spheres is the same as the span of real projective space. I'm not going to argue this, I'm just going to use this result. But really what you have to do is look at your sphere. You know how many vector fields, linearly independent vector fields, are on that sphere. You just need to check that those descend to the quotient RPN, where you mod out by scalar multiplication. And you can do this, there's like a construction using orthogonal multiplications and stuff, but hopefully you can kind of believe this. What I want to explain is that we have the same exact statement for projective span. It's a really cute one-liner, and it's going to use all the facts that we've learned so far. So we can practice everything. Step 1 is this corollary that I'm not proving. So we're assuming that the span of RPN is the same as span of the N sphere. The next step follows from remembering that spheres are simply connected. And we showed that for simply connected manifolds, span is the same as pspan. The next inequality comes from the fact that projective span of a cover is at least projective span of the base, where we're thinking of the n sphere as being the double cover or the universal cover of RPN. And then the final inequality follows from the fact that projective span of a manifold is at least span of that same manifold. So we have span of RPN on one side and span of RPN on the other side. So that means that these inequalities actually are equalities. And so the proposition holds. Okay. Are there any questions so far? I can't see the chat. Is everyone doing okay? Am I going to?
I have a question.
Yeah.
Hi, it looks like existence of k independent line bundles is not the same as existence of a k-frame. Can you explain that a little bit more? Thank you.
Yes, I can. Here, let me just go back a little bit. Yeah, I mean, this is something that you have to check. So a vector field on a manifold or a section of the tangent bundle gives rise to a trivial line subbundle of the tangent bundle. And this is something that you have to check. But the thing to remember is that to get a rank k trivial subbundle of the tangent bundle, you just need a basis spanning a k-dimensional vector subspace, right? So if you have k sections of the tangent bundle, and those sections for each point give rise to a basis of a rank k subspace of the fiber, of the tangent bundle, then that will give you a rank k trivial bundle of the tangent bundle. I hope that might help a little.
Yeah, but how is it different from like existence of a k-frame, which is, at each point it's a orthogonal frame of
well,
okay.
they are orthogonal. They have to be orthogonal. Are you worried about them being orthonormal, or maybe?
Oh, yeah. I guess I kind of know it. Yeah. Thank you.
Sure. No problem. Sorry. Let me get back to you.
Really quick. So one thing is I'm happy to keep an eye on chat for you, but then I also had a question about this radon-Hurwitz number, Hurwitz radon.
Yeah.
Just how computable is this, or is it easy to say? Or?
Yeah, so these radon-Hurwitz numbers, it just depends on, it's like a weird way of writing the number n. I can't remember, but it's like let n be a to the power of b plus, it's just some weird way of writing the number n. So you can easily like calculate these numbers. They're very computable is the answer. And thanks for keeping an eye on the chat for me. Okay. And yeah, please let me know if there are any questions, any other questions. So now we're to the point of, this is a slightly harder portion of the talk. Hopefully by now it's been okay. What exactly is my thesis problem, or one of my thesis problems? The first thing to say is that my supervisor, Mark Grant, and his collaborator, Dermot Crowley, extended the Hop theorem to hold for line fields. So they have this theorem that says a smooth closed connected manifold admits a projective one frame or a line field if and only if the Euler characteristic vanishes. So it's the same exact statement, you can just replace it for line fields. And the interesting thing was that physicists were using this result in their research, and they didn't really know that it was true that it held, and it actually did. So my supervisor was kind of like the physics cleanup crew here, and I'm kind of looking at the next step. So here I'm assuming the dimension of the manifold is bigger than 4, and I'm trying to find necessary and sufficient conditions for the projective span to be at least 2. And I should just say that there is some physics motivation for doing this, although I don't really personally care that much about the physics motivation, but soft matter physicists and synthetic chemists are interested in these biaxial pneumatic liquid crystals, which I think are really important in like electronics and stuff. And apparently you can use projective 2 frames to model these things. And so they're really looking for some kind of projectivized Hopf theorem in this case, although I really don't think there's any such thing. But for instance, I've been talking to some chemists in the department at Aberdeen, and they're working on this like self-focusing contact lens. And that's something that they need this for. So I don't know, there's just interesting reasons for studying this. So this is my problem. I'm looking for necessary and sufficient conditions for a manifold to emit a projective 2 frame. And my methods are obstruction theoretic. And the main thing that we need to do to see that this is an obstruction theory problem is to rework it into a lifting problem. So if you haven't really seen like classifying maps of bundles and stuff, don't worry about this. You can just believe this. But projective span of a manifold is at least k if and only if the classifying map of the tangent bundle lifts, as in this diagram here. So here is the classifying map of the tangent bundle of the manifold, and we're trying to reduce its structure group to this here. So you can kind of see this is the leftover rank n minus k bundle bit, and here are the k possibly non-trivial line bundles that we're trying to split off. And the fiber of this map here is a quotient of the Stiefel manifold of orthonormal k-frames in Rn by this action of z mod 2 to the k. So it's some kind of projectivized Stiefel manifold. So this is the picture to keep in mind. And I want to use Moore-Postnikov theory to factorize this vibration to try and solve the lifting problem. So I want to now just try and give a very brief overview of this kind of theory. I think it's actually, it gets a bad rap, but I think it's actually really elegant, and it's very useful in many, many situations. Even if you're doing like, I don't know, crazy homotopy theory or something, you might end up needing Moore-Postnikov theory at some point. And the general sort of machinery works kind of the same no matter the context. Before I get into this, I just wanted to say one final thing about this vibration here in this diagram. When you're doing classical Moore-Postnikov theory, you always require that the vibration be simple. And what that means usually is that pi1 of the base space of the vibration acts trivially on the homotopy of the fiber. But this vibration is very badly behaved in that pi1 of the base acts non-trivially both on the space of the fiber and on the homotopy of the fiber. So this is really bad, and there's kind of like double twisting going on, and it just makes things really complicated. And I really think that this is why no one did this in the 60s. It's a very classical seeming problem, but they just didn't have the tools then that we have now to try and tackle it. So we want to use Moore-Postnikov theory to try and factorize the vibration. Let's just consider an arbitrary vibration. Moore-Postnikov theory has been generalized so much that you only require F, E, and B to be path connected in the most general setting. And we want to try and factorize it into a diagram that looks like this. So I'll try and talk you through this diagram a little bit. Here's our vibration. Here's our lifting problem, the bottom triangle here that we're trying to solve. So just keep that in the back of your mind. And the upper bit is the Moore-Postnikov decomposition, where we have these spaces that I haven't explained yet. these lifts of P that I haven't explained yet. And then these here are the K invariants, which I'll explain in a second as well. So we require some things of this factorization. The first thing is we want it to commute. So what this says, the condition here, it says that Q1 is a lift of P. So if I do Q1 and then P1, that's the same as doing P. And Q2 is a lift of Q1. So if I do Q2 and then P2 and then P1, that's the same thing as doing P, and so on. Okay. The second thing that we want is a little bit more mysterious, but it's absolutely key to solving the lifting problem in the end. So what we require is that each Km is an M equivalence. So what that means is if you look at Qm, sorry, I think I was saying K, each Qm needs to be an M equivalence. So Qm, which is a map from E into ERM, if I look at the induced map Qm lower star and homotopy, I want that to be bijective through dimension m-1 and then surjective in dimension m. So Q1 needs to be a 1 equivalence, which means that it's bijective on path components. Sorry, I guess there should be an equal sign there. And then it should be surjective in fundamental groups and so on. Now, why on earth do we want that? It's really, really key to helping us solve the lifting problem. So I'll try to explain this. This is just a slightly simplified diagram. So suppose we have our vibration P. We have our lifting problem that we're trying to solve. And we've built a Moore-Postnikov factorization satisfying these two criteria here. Well, by the second criteria, if we look at the induced morphism of Qn, so this is a map from E to ERN, where n is the dimension of this manifold M. We required it to be an n equivalence, which means that it's bijective through degree n-1 in homotopy and then surjective in dimension n. And it's just a basic homotopy theory fact that implies that the morphism Qn hash, where we're homming out of M, is now surjective. If you don't remember this kind of thing, the only place I've seen it written down is in Spanier's old book on algebraic topology. I think it's in chapter 7. So if you're curious about that, you can look it up there. But what this means is that Postnikov theory has allowed us to kind of change the lifting problem game. So we had our vibration. We're trying to find a lift of this map F from M to B. And we could try and construct this by hand, but now Postnikov theory is telling us if we can construct a map from M into some high enough EI, depending on the dimension of M, the manifold, then by surjectivity of the appropriate QI, we'll be gifted the map we're looking for from M to E. So this is how you use this kind of thing to solve lifting problems. So now we just need to build a map from M into ERN, and by surjectivity of this QRN hash, we get for free a map from M to E that lifts F.
Sorry, can I just ask a quick question about the last slide? Does this say that somehow like you only have to check, say, at most in obstructions? Does give you an upper bound on how many obstruction classes or something you might have to calculate?
Yes, I guess that's true. This is a very good question. I think this might become a little clearer in a little bit, because the way that you construct this map eta that I've drawn here is in stages. So you first try and build a map from M to ER1. And if you can't do that, then you found the primary obstructions to the lift. If you can, then you can try and extend it to the next stage. And then you'll have found secondary obstructions, but there might be, possibly uncountably many or something secondary obstructions. So it can get really bad really quickly, but hopefully it's like computable, the amount of obstructions.
Cool, thank you.
Yeah, sure. So the next thing I want to try and explain, I don't want to go into too much detail. I'm sorry if it seems like a lot of detail, but we have this factorization that we want to build, and I want to just explore a little bit, how could we possibly build a factorization satisfying 1 and 2? So what I'm really trying to do is give you a sort of existence proof of Postnikov systems in just a very, very sketchy way. The first thing that we really need to remember is the homotopy fiber construction. So here's our map from E to B, our vibration P. And this is where the K invariants come in. So focus in on this map, W from B into C. This is our first K invariant. So we're trying to build what I was calling ER1 before, this space EW. And we want to build it as the homotopy fiber of this K invariant. I just want to comment on this space C for a second. C in like the classical Moore-Postnikov theory context is just going to be an Eilenberg-McClendon space. In the slightly less classical version, it could be a product of Eilenberg-McClendon spaces. For me, because my vibration is horrible, it's going to be a generalized Eilenberg-McClendon space or a product of such things. I don't really want to get into that, but really we wanted to just think of this W as some kind of cohomology class in the cohomology of B. And it might have horrifying coefficients or something, but it's just a cohomology class. So when I write things like this, just think of this W as a cohomology class in B. It's just some cohomology class. So given our vibration P, choose a cohomology class in B, we'll call it W, and we'll look at the path loop vibration over the codomain of this cohomology class W. Now we pull back the path loop vibration along the cohomology class W, and we obtain this space. This gives us a new vibration from EW to B with fiber loop C. And the upshot of this is that a lift from E to EW, which we might call Q, exists if and only if the composition of P and W is null homotopic. Or because we're thinking of W as a cohomology class in B, we can say that a lift from E to EW exists if and only if W is in the kernel of P upper star, the map induced on cohomology. That's a really useful way of thinking about it. And the reason for that is because of the universal mapping property of the pullback. So I've just written down this diagram here to try and convince you. You can see that a lift from E to EW exists if and only if there's a map from E into the path space of C, which is contractible. So making this diagram commute. So if I go from here to here and here, that's a pointed null homotopy of the composition of W and P. So you can hopefully be convinced. So, okay, let's go back to this, this picture here. We can now see how to build a commutative factorization. It's really as simple as doing this homotopy fiber thing. We have P, we choose some cohomology class K0 in B, which is in the kernel of P upper star in cohomology. We take the homotopy fiber of that K0, which gives us this space ER1. And because it was in the kernel of P upper star, we just for free get a lift Q1. And we keep doing this. So you find a cohomology class K1 in this space. You make sure it's in the kernel of Q1 upper star. You take the homotopy fiber of K1 and get this space. And for free, you get a lift from E to Q2 and keep going like this. We haven't, though, enforced this equivalence behavior of the QIs that we wanted. So this is the last thing I need to explain. I'm so sorry to talk everyone through these diagrams. So here we are. We have, I've left the vibration from E to B called P out of this picture. But suppose that we've chosen W, a cohomology class in B, and we've taken the homotopy fiber of that, giving us this EW. And that gives us this vibration P bar with fiber loops C. Now look at this lift Q, which exists because W was chosen to be in the kernel of P star. This Q, we want it to have a certain behavior. We want it to be bijective in homotopy through a certain dimension and then surjective the next dimension up. So we're trying to see what do we need to make that happen. Now restrict Q to the original fiber F, which sits inside E. And you can easily check that this gives you a map V from F into loops C. Now, turn V into a fibration, say with a fiber F sub V. You can then easily check that Q from E to EW is homotopy equivalent to a fibration with fiber F sub V. Okay, just believe me about this. So now visualize this Q, which we're thinking of now as a fibration with fiber F sub V. If you think of the long exact sequence in homotopy of this fibration, then you will see that the behavior that we're trying to get Q to have is directly controlled by the connectivity of this fiber F sub V. So if F sub V is like m-1 connected, then by the long exact sequence in homotopy, Q will be bijective through dimension m-1 and then surjective in dimension m, as we wish. So this is how we can achieve such a factorization. Okay. Final thing I need to explain is something I kind of already explained a little bit. Now that we've built the factorization, how do we abstract obstruction theoretic data from it? So we need to build a map from M into some high enough EI, and then that will give us for free a map from M to E, which we're looking for. We try and do it in stages. So we build a map from M into E1. We can do that if and only if F pulls back the first K invariant to 0 in the cohomology of M. If it pulls back to something that's non-trivial, then you found the primary obstruction to the lift. If F does pull back K0 to 0, then you can build a map eta from M into E1, although there might be many possible choices of such a map. But you choose one, and then you try and extend eta to E2. And you can do that if and only if eta pulls back the next K invariant K1 to 0 in the cohomology of M. But if it doesn't pull back to 0, you might need to just choose a different eta. And maybe that new choice of eta will pull back K1 to something trivial in the cohomology of M. So what we really need to compute is this sort of generalized invariant K1, where we look at where eta pulls back K1, but then we have to range over all the possible lifts eta. And that will give you a set of cohomology classes that lives in the cohomology of M. So if you can't compute this set, you can't really do much. You have to, at least to carry on, show that 0 is an element in that set. And unfortunately, it's not really possible to do this. I'm running a bit out of time, but I just wanted to mention that there exists this like really high-tech theory developed by Emery Thomas, where he basically says that there exist these mysterious classes in the cohomology of B, the base space of the fibration, and some kind of magical higher order twisted cohomology operation such that this holds. I'm not going to explain this, but by naturality, this basically gives you some hold on the coset that you're trying to calculate. So like maybe you have no hope of calculating this K1F, but maybe you can calculate the image of this mysterious cohomology operation. So that's kind of the idea that's going on there. I won't really explain that. Finally, I can show you my tower and try and talk you through a little bit of it. I'm sorry for all the horror about Postnikov theory, but this is kind of, well, this is what my tower looks like for one specific case. So I'm focusing in here on when M is non-orientable, and also when N, the dimension of the manifold, is even. I'm also interested in all the other cases, but let's just take this one, for example. So here's this fibration that I was showing you before. With fiber like a quotient of the Schiefel manifold, and we want to factorize that. It turns out that the first K invariant is just trivial. So I take the homotopy fiber of that and get this space. And this gives us a resultant lift Q1. And the fiber of that is more highly connected than the previous fiber. And this is the universal cover of the original fiber. This is just the ordinary Schiefel manifold of 2 frames in Rn. This fibration is sadly it's really badly behaved. and there's loads of crazy coefficient stuff going on. So the next k invariant needs to live in the cohomology of this space with some really weird coefficients. So these are the generalized Eilenberg-McClendon spaces I was telling you about. And I'm taking some kind of weird fibered product over a certain Eilenberg-McClendon space of those things. And it's just a little bit of a disaster. What I've written here is the k invariants. The identities of these classes are kind of under construction. My supervisor and I are developing this new theory of, or I guess potentially new theory of projective characteristic classes that are somehow like an obstruction to splitting off line bundles. So it's sort of another talk to explain what they are, but they should remind you a little bit of the twisted integer n-1 Stiefel-Whitney class and the twisted Euler class of some virtual bundles, if such a thing did exist. And that's that's all I'll say about that, really. And then the tower goes up a little. There's another k invariant. K doesn't really matter, but this is what my tower looks like. And I don't have the full statement for you yet because I'm still doing some horrifying spectral sequence calculations. But just for the punchline, I wanted to give you kind of a sample statement, because I can see the light at the end of the tunnel and I know what it's going to look like at this point. So the end result is going to look something like this. Give yourself two one-dimensional classes in the cohomology of M with Z mod 2 coefficients. Those classes are really the classifying maps of two specific line bundles that you're trying to split off the tangent bundle of the manifold M. And my result will look like if some certain mysterious class vanishes, which I'm working on describing this class, and a complicated equation holds, where that equation has terms of this form. So here is the powers of the integral twisted Stiefel-Whitney classes of the manifold, and then you have powers of those two one-dimensional classes. If all of that stuff happens, then the manifold admits a projective two-frame, and vice versa, because it's a necessary and sufficient condition. Okay, I think that's all I had to say. I hope that was understandable to everyone. Thank you so much for listening. It's really fun to get to talk about what I'm up to.
Let's thank Baylee for a wonderful talk. So feel free to clap or use your clap emoji in Zoom. A lot of clap emojis, great. Yeah, does anyone have any questions for the speaker?
I have a question. So is there any hope to see these projective characteristic classes as obstruction classes to something? Is that the way you're trying to construct them, or?
Yes, I was originally, so for instance, the Stiefel-Whitney classes, you view those as obstructions to a section of the Stiefel bundle, right?
Yeah.
I was trying to do that with these as well, but it doesn't really seem to be working out like that. It's all a bit strange, but I completely agree with you. I feel like that's what they should be, obstructions to the section of some fiber bundle, but it doesn't seem like it's working out that way.
Okay, thank you.
Maybe I should just mention on that note, sorry, I recently found this book by Koshorka that I briefly mentioned. I finally got my hands on it, and he has a completely opposite approach, and I don't really understand it because it's all this normal boardism stuff that I don't have a ton of background in. But the invariants that come out of his approach, I'm 96% sure that they might be Poincare dual to mine. So I don't know, maybe I'll have a better answer to that question once I understand Koshorka's approach.
Cool. Yeah. Other questions? right, and nothing in chat. So I guess let's maybe thank the speaker once more and close out for the day. And I will stop the recording.